Well, I am going to do a presentation in English. But some of you know who I am, but some of you don't know who I am. So my name is Natàlia Climent. I'm a research engineer here working at the geomechanics group. And I am using GPFEM here, but today I'm not going to talk about the work I'm doing here, but I'm going to present the work I did in one of my postdocs in Lisbon, that it's the development and the implementation of three-dimensional hybrid-Trefftz finite elements for saturated porous media. And I am presenting that because I thought, well, these are non-conventional finite elements, so we are not used to this kind of finite elements, and they are useful in some specific problems, and maybe someone it's of interest of someone that maybe want to use them or want to implement them in another platform. It is supposed to be okay. So first I'm going to talk about my background, then the project that I was working in. Then I am going to talk about the development of the equations and the functions of the finite elements. Then I'm going to talk about the platform, the implementation, and the simulations and the testing we performed. And finally, I am going to talk about, well, I am going to ask what other applications can we find, and I'm going to give you the references. It's like that. I am a physicist. I did a master's degree in geophysics. I did my PhD here at UPC in geotechnical engineering. During my PhD, I used the discrete element model, and I coupled it with computational fluid dynamics to model sound production in our wells. And after that, I worked as a research fellow at the Instituto Superior Técnico in Lisbon. Then I worked as a consultant at Amphos 21 in Barcelona. And finally, before coming here, I worked as a research associate at Imperial College London, working doing some implementations in an in-house code they have for simulations for THM problems in elastic porous fractured media. So as I said before, I am going to talk about the work I did here in Lisbon. I'm not here, here is Barcelona, in Lisbon at Instituto Superior Técnico. I am not learning this. I worked in the CEN-DynaGEO project. And before talking about the project, I am going to introduce these Bender element tests that were the ones that we wanted to simulate. These tests try to measure the properties of the soil, the small strain shear modulus. And this is a scheme of the experimental apparatus. The soil sample is set inside of a mold. Bender element is installed in the base plate, and an electrical signal is converted into a vibration. So the Bender element transforms the electrical signal into a vibration. So this vibration travels across the soil sample vertically, I mean perpendicularly to the vibration, and also towards the lateral envelope. The wave that is traveling perpendicular is the shear wave, and the others that travel in the other directions are the P waves. And the theory is simple. You have the shear wave, you can calculate the time travel across the sample, and you say, okay, you can calculate the time travel, I calculate the velocity, so with the velocity of the shear wave, I can calculate the shear modulus. But it's not as simple as that, because there are some difficulties in the interpretation of the output signal due to the high frequency damping, energy radiation, or boundary reflections. So because of that, The aim of the CEN-DynaGEO project was to improve the interpretation of these tests. How? The aim was to create a toolbox, a numerical toolbox that performed a lot of tests to estimate the best wave fit. It was a kind of back analysis or calibration. So you perform a lot of tests. When you have a wave that fits the one that you get in the experiment, you know that this numerical simulation has been performed with the shear modulus that you want to measure. The problem is that you cannot do that very easily with conventional finite elements because you usually have very high frequencies in this kind of experiments, like 1,000 hertz, etc. So you need to refine the measure a lot if you use conventional finite elements, or you cannot even simulate them. So the idea was to use these non-conventional finite elements, the ones that I'm going to present afterwards, to be able to perform all these tests in a reasonable time in an easy-to-use toolbox. The 2D version of this toolbox was developed by the PI of the project, that was Professor Ion Moldovan. And my work in the project was to develop the same functions, but in 3 dimensions. So what are the main differences between conventional and Trefftz finite elements? The Trefftz finite elements satisfy the domain equations inside of each one of the finite element. So it's problem dependent because you are solving the equations, and it's independent of the nodes of the mesh. So it needs a less refined mesh, and it's less sensitive to high frequencies. So as I said, you have to solve the domain equations in the finite elements. And for a porous, homogeneous, and elastic material under small deformations, the equation that has to be satisfied is this one. This is the elastodynamic equation. It's a collapse of 3 equations, the equilibrium equation, that we are supposing that the body forces are null, the compatibility equation, and the elasticity equation. And we are working using the Biot's theory. So we are dealing with a biphasic medium. So these U that you see here are not only the displacements of the solid, but also the C pages of the fluid are considered. And it happens the same with the stresses. We consider the stresses of the solid and also the pore pressure. This M is the mass matrix, this D is the damping matrix, and the K is the stiffness matrix. And this is a differential operator. I think it's called the adjoint differential equilibrium operator. And the boundary conditions that we are considering are the Neumann and Dirichlet boundaries that everyone knows, the ones where you impose tractions and displacements. We are considering absorbing boundaries. Absorbing boundaries are the boundaries where the waves can travel through them. So it's like you are simulating a semi-infinite domain, and also elastic boundaries. So as you see here at the bottom right, we have displacement and stresses and pore pressure that depends on space and time. So first you need to discretize in time, and we suppose that the displacements, as well as the stresses and the strains and everything, can be expressed as a combination of a function, a displacement function that only depends on space, and a kind of weight function that only depends on time. So we use the expansion in wavelength basis that yields a series of spectral problems in space. Each spectral problem has a frequency. This frequency is usually an imaginary number. And finally, what we get is the general Navier problem in space. This transformation, I synthesized this here. I mean, it's more complicated than that, but it's like doing something similar than a Fourier transformation. the initial conditions are always zero, are always considered zero, and there is a kind of weird thing that you only consider one time step. So all the simulation time is only one time step, but you divide the time step into different time points, and each time point is related to one spectral problem. So after doing that, you only have to solve an equation that only depends on space. The displacements are approximated using this matrix U that collects the Treff basis that satisfies this domain equation, that is the Navier problem we presented before. So this U collects approximation functions that are actual waves. So they are the solutions of this problem. So we have, in this case, because we are dealing with biphasic media and also 3 dimensions, we have 2 compression waves because we have fluid and solid, and 2 shear waves because we have 3 dimensions. So I am going to try to synthesize a little bit this part. There are some functions that are going to appear here. This is the equation that we want to solve. We consider first that the displacements can be expressed as a combination of the gradient of a scalar potential for the P waves and the rotational of a vector potential for the shear waves, for the solid and for the seed pages of the fluid. So doing some calculations, this is the result for the scalar potential for the P waves, only for the solid. I'm not going to show all of them because we consider them like proportional. And if someone wants to go deep to that, you can go to the reference. These are the potentials. The potentials depend on these are the spherical Bessel functions, and these are the spherical harmonics. And the result is computed, is calculated in spherical coordinates, as you can see here. This beta is a parameter that I am not going to explain here everything. It's a parameter that is defined in the reference. So if you want to go there, you can find every detail there. And you can see here that we have an n. The n is the order of the spherical Bessel functions, and the n goes from 0 to whatever number you want to choose. And the m goes from minus n to n. So this, after that, we solve the equation for the shear waves. And these are the 2 shear waves, the 2 potentials for the shear waves, each one of the coordinates because they are vectors here. These are a little bit more complicated, as you see. But with all of that, you can compute then the displacement, substituting there in the displacements equation. And then with that, you can compute the strains and the stresses. I didn't put everything here because you can imagine they are derivatives of all of that. So they are large, but all of the functions are in the paper we published. So finally, the displacements and the stresses can be computed as a combination of these functions, these displacements that we calculated with the functions, as a combination of all of them. For example, if we define when we want to perform a simulation, we define a capital N that is the P refinement. And with this capital N, you are going to combine all the functions that go from n equals 0 to n equal capital N. And this is how you build your calculation of the displacements and the stresses inside of each one of the finite elements. So you can imagine if you only consider order 0, for example, it's not very smart, but you want to consider only 0, you are only going to have one function, and this is going to be your result. But if you consider more orders like 2, you are going to calculate 0, 1, 2, and you are going to combine all of them. So after calculating all these functions, I implemented the functions in a 3D version of the this free high-T platform. It existed before in 2 dimensions. I had to change some things because the functions in 3 dimensions are more complicated. So it was not straightforward, but it was expanded for 3D. It was implemented in MATLAB. This was a decision made because most of the students in Portugal learn MATLAB, so it was easier for the PI to, because a lot of students, master's students, work in the code too. So they sometimes for their final final project, they have to implement something. So it was much easier. And for 2 dimensions, you can solve transient problems defined on solid and saturated and unsaturated porous media, and for 3 dimensions, solid and saturated porous media. And after that, after implementing all the functions and everything, we wanted to test the implementation and the functions. So first, we performed some convergence tests. So we performed tests of a single frequency, a single spectral problem with a known analytical solution, and we compared the results with the analytical solution. It was a simple problem. The YX is the mechanical energy of the finite elements divided by the analytical mechanical energy. So it has to tend to 1. The x-axis is are the degrees of freedom. The degrees of freedom are a combination of the mesh refinement and P refinement. So if you increase the number of mesh elements you have, the degrees of freedom increase. And if you increase the orders of the functions I presented before, the degrees of freedom increase. So the tendency was to tend to 1 when the degrees of freedom increased. After that, we performed simulations of a vertical shock wave, and we compared the results with the ones performed with the 2 dimensional platform. We imposed a load on the top boundary during 0.0008 seconds, and we imposed 2 different boundary conditions at the bottom boundary. Dirichlet boundary conditions with a null displacement and absorbing boundary conditions. And we compared the results with the 2D version of the platform. So the 2 of the left are the ones, I'm sorry, because there's something here. So these 2 on the left are the ones with the Dirichlet boundary at the bottom boundary. The one on the left are the results at different time points for the 2D version of the platform, and the one on the right are the same results at the same time points using the 3D version of the platform. And the 2 ones on the right it's exactly the same, but with the absorbing boundary at the bottom, with the absorbing boundary conditions at the bottom boundary. So we can see here, these are the vertical stresses. We can see here that the results are exactly the same. You can even think that maybe I copied the image. I didn't. But they are the same. You can see here that there are 2 P waves, the P1 that travels faster and the P2. And when you use Dirichlet boundary conditions, the wave reflects. And when you use absorbing boundary conditions, the P1 disappears. And finally, we perform the simulations of the Bender element test. The geometry was a cylinder with a height of 50 millimeters and with a diameter of 200 millimeters. We installed a Bender element in the middle of the bottom boundary. This Bender element vibrated in the X direction at a frequency of 100 Hertz, but only 1 cycle was considered. So the Bender element was not vibrating all the time, only vibrated 1 time. So these are the results. This is the XZ plane at y equals 0. So, and these are the horizontal displacements in the x direction. So here we should see how the waves travel moving this way. Well, is this supposed to work? Yes, this is rubbish. Sorry. So you can see here that now the Bender element is moving in the positive direction, and the shear wave is arriving now on at the top boundary, and there are two P waves traveling the other directions, and now it's moving the other way at the negative direction. And here we can see this is the XY plane. This is on the left, is very close to the Bender element, and on the right is very close to the top boundary. And these are also the horizontal displacements in the X direction. So here the refinement is not very high, I must say, because, well, after that we performed simulations only with half of the geometry, and it was much better, but still. So this is where my work finished. When I was there, we couldn't go much deeper, but it was it was inside of the plan of the project. But the question is, okay, we have used that for these Bender elements, and these are elements that have limitations, of course, because we are supposing that the medium is elastic. Of course, this is a limitation. I did that for saturated media, but it can be expanded to unsaturated media. And, well, maybe they are not as good as conventional finite elements. We are supposing that there are small deformations, etc., etc. But they are useful for something very specific, that it's simulating these high frequencies. It can be coupled with a conventional finite element model. And, well, I mean, when we were finishing the project, we were thinking about other applications. We were thinking about maybe trying to apply it for rail track infrastructures, because during, I don't know how to explain that now, but there are loads with high frequencies involved, and we were thinking about trying to implement that, or to simulate something like that, but we couldn't. But it is an idea. And that's all. These are the references. These are the papers we published during all the project. The fourth one is the one that I presented today. The second one is the same, but for only one phase, for solid. And the last one is the one that explains how the platform works. I think it's a very nice paper to understand how the platform works. And the other ones are conference papers. And, well, that's all. Thank you. And if anyone has a question or comment, I'm glad to answer or comment. I don't know. Yes, yes.
I have a question. When, well, two.
Two questions.
Yeah. One of them is what controls the discretization of this thing? Because you have talked about choosing the extent of the base, but then the spatial discretization is linked to what?
Well, in this case, for example, sorry, I wanted to drink water because I had this right, but for example, it's true that you need to remesh and to refine the mesh when in places where, for example, very close to the vendor element, we have to refine the mesh very much. Not as much as you would need with conventional finite elements, but it depends also on that. If you increase the orders of your functions, you are not going to need to refine the mesh as much. But if you have a very, I think it's quite similar to conventional finite elements. So you need to refine the mesh where you are going to have changes very quickly.
Yeah, but is there any specific criteria? It's not frequency, or is it frequency, or what is that? What
No, well, I think it was more like, you know, you test a little bit and you play a little bit with that. But I usually had to refine when I was very close to the
source?
exactly, yeah. It is something for the boundary condition where, yeah, the source.
My second question is, you said that this thing can be conflicted or integrated with conventional finite elements, but how do you envisage that? I mean, like having two separate domains, one of which is conventional finite elements and the other
exactly
is Hybrid-Trefftz, or
you cannot
solve different equations in the same domain.
No, you have to you need to have two separate domains, but in contact, of course. But the finite elements cannot be mixed. I mean, they have to be different. I don't know how to do that. I know that you can because.
Are there any precedents of that?
I think so. I think so. But we should, if someone is interested in that, I should talk to John Moldovan because he's sure. I mean, it has been done that, but not for porous materials, but for solids. Because this kind of finite elements are more used in structures and things like that, so for solid, but not as much for porous media or soils. Yeah.
Just wondering, can you comment on how this method actually compares to finite elements, higher order finite elements? For example, if you perform the convergence test and instead of the Trefftz method, you use higher order finite elements, does Trefftz method converge faster or is it more sparse, or what's
I didn't do that, so I cannot show you.
Do you know what the convergence rate actually is?
I didn't use, I mean, it even can be different depending on the finite elements you are using because there's not a simple conventional finite element model.
Just like high order.
I didn't test it. We in another paper, one PhD was compared results of a simulation with another one with conventional finite elements, but we didn't test the conversion test, for example. So, yeah, it could be interesting.
Another question, if I may, about the time discretization. You said you're using some form of wavelength transform. You also mentioned it's kind of similar to Fourier transform. What's the motivation of using this one rather than just Fourier transform?
Yeah.
Specific advantage in the context of this method.
It has advantages, and the study of that was done by Professor John Moldovan before for 2D. And so we decided to use the same because they work much better with waves, the one we use. It can be done with Fourier Fourier transformation because I mean in his thesis he explained also that, and I think that he tested both, but it's much easier and it gives better results with this one. I don't know if there is a question online. I don't know if you see that. Can we see that? No. Okay. So if no one has any other question, I think that we can finish here. Thank you and bye.
Thank you.
Thank you.